Have you ever been in the middle of an important task on your computer, only for an application to suddenly crash or freeze? It is incredibly frustrating, and in critical systems, such failures can have serious consequences. To prevent these disruptions and ensure continuous operation, software engineers employ a set of powerful techniques known as fault tolerance. Software fault tolerance refers to the ability of a computer system to continue operating without interruption, even when one or more of its components fail. The most common approaches to implementing fault tolerance include redundancy, error detection and recovery, and inversion programming. These methods are designed to build systems that can withstand unexpected problems and keep running reliably. The fundamental principle behind these approaches is to manage system failures gracefully rather than letting them lead to complete collapse. Redundancy, for example, involves having backup components or processes ready to take over if the primary one fails. Error detection and recovery focuses on identifying issues as they occur and restoring the system to a valid state. Inversion programming, a more complex strategy, aims to eliminate common design flaws by using multiple independent implementations of the same function. To put these into practice, redundancy can manifest as having duplicate servers running in parallel, with a load balancer distributing requests and redirecting if one fails. Error detection often involves checksums or heartbeats to monitor component health, and recovery might include automatic restarts or rollbacks to a last known good configuration. For critical calculations, inversion programming would involve 3 or more development teams independently building the same software module, and then using a voting mechanism to determine the correct output, thus mitigating the risk of a single programming error bringing down the system. A fascinating aspect of fault tolerance is its connection to the concept of graceful degradation, where a system can continue to operate, albeit with reduced performance, rather than failing entirely. This is often achieved through techniques like checkpointing, where the system periodically saves its state, allowing for a quicker recovery to a recent stable point instead of starting from scratch after a failure. Another advanced method is Byzantine fault tolerance, which addresses situations where components might fail maliciously or send conflicting information, ensuring consensus even in untrusted environments. Understanding these fault-tolerant strategies is incredibly valuable for designing robust software that stands the test of time and unexpected events. By proactively incorporating redundancy, sophisticated error handling, and diverse implementations, developers can build systems that not only recover quickly from failures but also provide a stable and uninterrupted experience for users, bolstering overall system integrity and trustworthiness.
If this helps you fix faster, like, subscribe, and keep debugging with us.